Right. So in the last class, we did multiple conversion from one form to the other. So we will continue. We last time we did a decimal to all different types of conversions, and then we also did from all different types of conversion to decimal conversion. We also looked at the representation of fractions, right? Say, for example, how do you convert a decimal number to a binary if you have the integer part and the fractional part. Integer part you will multiply with the positional weights, or you will divide it by the uh, base of the required number system. Say here in this example, 41 is repetitively divided by the base 2, which means we require a binary number system here. Similarly, the fractional part you will multiply. So here you will divide and you will multiply for the fractional part. So that we saw in the last class. And we saw the octal to binary to octal number system. In fact, they are slightly simpler in the sense all you need to do is separate them into different groups. So here you need to separate into group of three. Why group of three? Because in case of a binary number system, 2 power 3 is 8. So hence for an octal, since we have 8 different symbols, we are grouping them into 3. In case of a hexadecimal number system, we are having 16 symbols there, and hence we are grouping them into 4. When required, this doesn't work. Okay, so we used to group in terms of 3 like this. Okay, all right. Okay, now let's move on to, and how do you normally remember the positional weights is normally the first, that is this particular positional weights, its positional weight is 1, okay, and the next positional weight is 2. Since I'm using a highlighter, it is very thicker, I cannot change my pen. Let me try notes. Okay. System is very slow. Yeah, okay. I think I'm back to digital electronics. Okay, so uh, you have octal number system, right? And you have binary number system. In case of a octal number system, we have 8 symbols: 0, 1, 2, 3, 4, 5, 6, and 7, right? And how do you represent in terms of binary? 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So immediately you might question, how did I get this number sequence? How did I get this number sequences? Each binary bit has got a positional weight here. Each binary bit here, they have got, okay, so each binary bit here, they have got different positional weights. On those particular lines, the least significant bit will have a weight of 1, and the next bit will have a weight of 2, and the next bit will have a weight of 4, and subsequently it will keep on adding in terms of 2 powers. So 2 power 0, 2 power 1 is 2, 2 power 2 is 4, 2 power 3 is 8, and then 16, and it will keep on going on. Since we require only 3 digits three binary digits for our representing octal number system. If you look, these are the positional values. So 0 is represented as 000. 1 is represented as we can represent with just 1. So which means this 1 multiplied by this 1 will get you 1. And we need 2. And out of this 1, 4, 2 and 1, if you need 2, obviously you can use directly this particular positional weight. Hence this is 1 here. Okay. And you need 3. And what combination of these 4, 2 and 1 can make it 3? Only the combination of 2 and 1 can make it 3. That is 2 plus 1 is 3. So that is why it is 1 here and 1 here. And you need 4. So 4, 2 plus 1, you can make only 3. So you need, since you need 4, only this particular combination, that is 4 needs to push 4's positional weights to be 1 and rest to be 0. And similarly 5, 4 plus 1 can make 5. So hence the position corresponding to 4 is 1 and 1 is 1. 6, 4 plus 2 is 6. So positions corresponding to 4 is 1 and 2 is 1. And 7, 4 plus 2 plus 1 is 7. Hence all three are 1. Okay, so like this you will remember the positional weights, decimal values. Now we saw this in the last class. How do you combine first? If you want to combine, all you need to do is convert binary to octal. You combine three bits. So this 3 bits, these 3 bits and these 3 bits we saw in the last class. And if the number of digits is not sufficient, and as this particular case, all you need to do is add 0. Similarly, on the fractional part, you need to add zeros towards the leftmost side, rightmost side. Here you will be padding the zeros to the leftmost side, rightmost side to the fractional part, and leftmost side to the integer part. Now, octal to binary. Again, it is the same. If you have a number which needs to be represented from octal to binary, right? If you want to represent from octal to binary, it is fairly very simple. Say I have a number 237. Okay, and how do you represent? 2 will be represented as in three binary bits. So 2 is represented as 0, 1, 0, and 3 is represented as 0, 1, 1, and 7 is represented as 1, 1, 1. Okay, now any other number, maybe 0, 1, 5. This will be represented as 0 will be represented as 0, 0, 0. 1 will be represented as 0, 0, 1, and 5 will be represented as 1, 0, 1. Right? So from this particular table, you can use the binary bits. So similarly here, an example here, 673.124. So how do you represent 4? 4 is represented as 100. 2 is represented as 010. 1 is represented as 001. And you have this decimal here. And 3 is represented as 011, 111 for 7, and 110 for 6. So this is how you convert binary to hexa. And now let us do octal to binary. Now binary to hexa. As you know that hexa has got 16 digits, right? You have got 16 digits. And in terms of binary, what makes it 16? Only 2 power 4 makes it 16, which means that you require 4 bits to represent the 16 hexadecimal symbols. So hence, you will be representing the hexadecimal values with binary in terms of 4 bits. So now again, we will go back to the positional weights here. What is positional weights? Say you have here, if you have hexadecimal value, how are they represented in terms of binaries? Let me make a table here. So let me insert a table directly. Okay, if I touch any other thing, it gets slower. So I need Okay. I need 2 columns. I need 16 rows. Okay. Okay. So this hexadecimal values. What are the symbols I have? I have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F. Okay. A means it is 10, B is 11, C is 12, D 13, E 14, and F 15. Sorry, is 15. Now, all I need to do is I have to convert these into binary. You know the positional weights, right? It is 2 power 0. I'll write here 2 power 0, then 2 power 1, 2 power 2, and 2 power 3 in this particular case. 2 power 0 corresponds to 1. 2 power 1 corresponds to 2. 2 power 2 is 4 and 8. Now, I have to create a binary sequence for this. So 0 is represented as, because I do not want to have any of these weights. So it is 0, 0, 0, 0. Now 1. 1, I have a positional weight 1 here. So I will have 1 here. Rest all values will be 0. 0, 0, 0, 1. Similarly 2, I have a position 2 already here. So rest all will be 0 here. Now I have 3. So what makes me 3? This 2 plus 1 makes me 3. So these positions will be 1 and 1. Rest all will be 0. 4, I am already having a position of 4 here. So this will be 1 and it is 0. Rest all will be 0. 5 will be 4 plus 1 will make 5. So 4 position and 1 position will be 1. Rest all will be 0. 1, 0, 1. 6, 4 plus 2, that is these two will make 1. Rest all will be 0. 4, 7, 4 plus 2 plus 1. So which means these 3 bits will be 1. The most significant bit will be 0. Now 8. 8 will be 1, 0, 0 and 0. Okay. So now 9. So since I'm scrolling down, let me write the weights again here. So weights are 8, 4, 2, 1 is the positional weights. So what makes it 9? 8 plus 1 will make it 9. So first MSB and your LSB will be 1, rest all will be 0. So 10, what makes it 10? This 8 plus 2 will make it 10, right? So 1 and 1, rest will be 0. So 1, 0, 1, 0 represents A. Similarly, B. So it is 8 plus 2 is 10. We need 11 here. So it is one more 10 plus this 1. So this position, and this position will make it 1 and 4 will be 0. So C is 12. What makes it 12? This combination will makes it 12. 8 plus 4 is 12. So it is 1, 1, 0, 0. Likewise, 1, 1, 0, 1, 13, right? So 12 plus 1 is 13. Then 12, 14. So what makes it? So these three combination will make it 13. So 1, 1, 1, 0. And finally, we need 15. So 8 plus 4 is 12, 12 plus 2 is 14, 14 plus 1 is 15. So all 5 bits will be 1. So this is how you create a hexadecimal table, hexadecimal to binary table. Okay, right. And this kind of coding is called as 8421 coding. Okay, so this is called as an 8421 coding. Why 8421 coding? Because we are using the positional weights as 8, 4, 2 and 1. Likewise, there are many different kinds of positional weights. Now, let's do a very simple exercise. Okay, so the answers are already given here. Maybe I'll create one more. So how many rows? 1, 2, 3, 4 columns and 5 rows. Let me create one more. Insert 4 columns and 5 rows. Okay. Now, so this will be my decimal values. This will be my binary. This is going to be octal, and this will be hexadecimal. So you will have to fill up this one. Decimal is 33, and you will have to fill up what is the binary bit. So binary bit, how do you do it? Decimal to binary, you will have to successfully keep on dividing it by 2. So how do you do it? Is 33 divided by 2 is 16, remainder is 1, and then 2, remainder 8, sorry, remainder is 0, 2, 4, remainder 0, 2, 2, remainder 0, and then further dividing it by 2, 1, remainder 0. So likewise, if you look, what is the equivalent decimal value here? So sorry, the binary value here, it is 1, 0, 0, 0, 0, 1. Okay, so this will be your binary value. Now, how do you convert it into octal? What is the equivalent octal value? If you want to convert from binary to octal, all you need to do is divide the bits into 3. So this 3 bits I can combine and this 3 bits I can combine. So what will be the equivalent value here? So 100 here, it represents 4 and 001 represents 1. So 41 is equivalent to octal. Now for hexadecimal values, all I need to do is I need to combine this into 4 bits. So these 4 will be combined and there is 2 and remaining 2 zeros I will pad up. So my answer here for hexadecimal equivalent will be 100010. What is 0010 here? 0010 corresponds to 2. So it is 2 and 0001 corresponds to 1. Please note that all these numbers, they might look like a decimal numbers. So what you should do, you must add their base value here. You must always write to the base 2 here, to the base 8 here, and to the base 16 here. Okay. So likewise, if you fill up the rest of the table, say for example, 1110101. So 1110101. Okay. So what is the equivalent decimal value? What you should do? In order to convert to the decimal, you will have to multiply it with the positional weights, right? So this positional weight is 1, this positional weight is 2, 4, 8, 16, 32, and 64. These are the positional weights of this number. So what must be this particular number? You just add those numbers wherever you are having ones. So I'm having 64, I'm having 32, I'm having 18, and then I'm having 4 and 1. So if I add all these things, how much? 6, 14, 18, 19, 9, remainder 1, 10, 11, and 12. So 129. 129 will be the decimal value. I hope I'm right. Oh, 117.
Sir, there is 16 over here
Uh,
instead of 18.
oh, yeah, yeah, yeah. So it should be 16. Yes, it is 16. So, okay. So then 16, 34. Yes. So it is 10, 12. So 6, 12, 16, 17. Yes. 7, remainder 1, 9, 10, and 11. Yes. 170. Okay. So this is 170. And octal, obviously, you combine 3 bits here. So if you combine 3 bits, this 3 can be combined, this 3 can be combined, and this 1 is separate here. So this 1 can be written as, you can pad 2 zeros in front of this 1. So this corresponds to 1. And this 110 here, this 110, it corresponds to 6 here. 6, and then 101 corresponds to 5. Okay, and hexadecimal equivalent is, all you need to do is combine into 4 bits here. So if you combine into 4 bits, the 010, always look from your LSB. So 010 and then 111. So this equivalent is 111 is equivalent to 7 and 010 is equivalent to 5. Again, please don't forget to write the base. So this base is 10 here, this base is 2, this base is 8, and this base is 16. Okay, so likewise, let us go back to the PDF. So 703 is the given octal number. Okay, so this answers are in black here. Answers are in black. So the 703 is the given number and solution is already there. So what you should do is you have to first convert 7 corresponds to 111, right? 0 corresponds to 000 and 3 corresponds to 011. Similarly, and how do you convert from octal to hexadecimal value, right? So for this, you have to convert to decimal and then from decimal, sorry, to binary, and from binary you have to convert back to hexadecimal. How to do that is, now you have converted into, you have converted the octal to binary bits, right? Now what you should do is, with the available binary bits, create 4 bit groups. So this 4 is done and this 4 is done. So, and I have only 1 remaining. I can pad 3 zeros in front of it. So 1 corresponds to 1, 1100 corresponds to C, and 0011 corresponds to 3. So first I have to convert this into binary, and from binary I will convert to hexadecimal. Okay. So similarly, the last example here, if I have 1AF, again the case is same. If you want to convert to octal, then first convert to binary. Okay, so combination you can see here that 1 corresponds to, so from the back you can write. So F is 1111, A is 1010, and then 1 can be written as 0001. Okay, and after you convert to binary, again do create a group of 3 and then convert to octal. So now you create a group of 3 here. This 3 is done, this 3 is done, and then this 3 is done. 110 corresponds to 6, 101 corresponds to 5, and 111 corresponds to 7. And decimal though we have already seen multiple times. Okay, and the shortcut that I already said you, it is already written here. What does that mean is, in case you want to convert from a binary bit to a decimal value, quickly what you can do here is, if say the binary bit is 1101. So what is the equivalent decimal value? I just did here, right? By adding, I substituted the positional weights here and I added here. So similarly, the same example is given here. Say 1101 is given. Okay, so this is what, this is a binary value. This binary, if you want to convert to decimal, then what you should do is, what is the position weight of this least significant bit? It is 1. Then this is 2, 4, and 8. Okay, and how did you get this? This is an 8421 number system. 8421 number system. And how did you get this? You got this by positional weights of the weights of 2. So 2 power 0, so 2 power 1 here, 2 power 2, and 2 power 3. Now, where do you have ones? I am having 1 in the 8th position weights. I have 1 in the 4 and 1 in the 1. So what is 8 plus 4 plus, this is 0. This 0 multiplied by 2 is 0 only, right? So 0 plus 1. So corresponding to 8 plus 4 is 12, 12 plus 1 is 13. So that is how, this is a slightly a shortest method which you can follow to find the, to convert from binary to decimal. So yes, this is what is written, and 13 can be represented as 1, 1, 0, 1. Similarly, the reverse way is also possible. Okay, so if you have 13, we created the hexadecimal table, right? So you can also follow the same thing. Okay, now whenever you are converting from decimal to binary, that is this particular case, always give priority to the highest weight first, which means that if you are having 13, don't give priority from least significant bit or something. Whichever is the highest value, enter 1 there. If I'm having, say for example, I'll give you a random example here. Say I'm having 45. Okay, I'm having a decimal weight of 45. So what are the positional weights that are possible here? It is, I will have the positional weights that are possible are 1, 2, 4, 8, 16, 32, 64 is not possible, right? Why 64 is not possible? because 64 goes beyond 45. So only till 32 it is possible. So first priority what I should give is, I should give priority to the highest value, which means 32. So I will put 1 here. Don't try to do the other combinations. So first I will put 32. Then what I will do is 32 plus 16 possible? So 32 plus 16 will give me 48, which will again go beyond this. So what I will do is I will put to the next highest value, which is 8. So what is 32 plus 8? I got 40. Then I will give priority to the next highest value. Now 44. 44 and 44 plus 2 will not get me 45. 44 plus 1 will get me 45 and rest all 0. Okay, so this is how I easily convert. Instead of doing this particular division, I will follow the simplest method. Why this is easier is because if I give you this particular number, say 248, 248, 248, you have to keep on dividing by 2 again and again and again like this. Instead, what you can do is identify the positional weights. What are the positional weights possible? 1, 2, 4, 8, 16, 32, 64, 128. I am writing in 2 powers, and then 128, 256. 256 weight is not possible because 256 is going beyond 248. So I will have to just write once subsequently like this. 128 will have the first priority 1. 128 plus 64. 128 plus 64 will get me what? So 2, 3, 8 and 10, 11, 2. So 212 I'll get. So I can give 1 here. So 212 plus 32 will go beyond 48, I believe, right? So 212 plus 32, it is 4, 4 and 2. It will go beyond. Oh, it is, no, I'm getting. So 232, I will have 244. Remaining 4 is there, right? So I can put 1 here, 0, 0. Right? So this will be the binary equivalent for this 242 for 248 number. Okay. So any doubts here? Okay. So thank you. Now, yeah. So this is the explanation that is given here. All right. So in case of so far what we have seen is still hexadecimal number, we have 4-bit number system, right? So which means that we are able to represent 16 symbols. There might be possible that you will have n-bit number system. N-bit number system, in the sense, what does it mean is this bit size will determine the storage capacity. Say for example, you might have come across 128-bit encryption, right? What do you mean by that? Say for example, you might have suitcases. When you have a suitcase, when you have 3 dials, when you have 3 dials, what is the maximum number that is possible? Maximum number that is possible is 999. So even you forget your number key in your suitcase, if you try 999 times, you will be able to open the lock, right? So if, say for example, your password, if you are giving as say 5-digit password, some, if you are giving some K, B, 2, 3, if this is your password, then, and this is a 128-bit encryption password, what does it mean is these are encrypted, these are coded into 128 bits, starting from 0, 1, 2, 3, likewise till 128 bits it's possible. So if anybody wants to crack your password, then they have to run a code having a loop of power 2 power 128. So these many times, only if you run, you will be able to find out this particular number. You can search, how does the password cracking system work? Say for example, if there is a PDF file and if it is password protected, there are websites which can open those particular passwords. They can, and how is that particular possible thing is possible is, this is the technique they will follow, right? So they will run the code for 128, the combinations for 2 power, if it is 128 bit subscription, encryption, they will run for 2 power 128 times. So roughly, what is this particular value? Anybody can quickly use the calculator, or I can use Google. Quickly, my system is slow, so can anybody use 2 power, what is 2 power 128? Yeah, so this is the value. I hope my screen is visible. So this is the value, that is 3.4028 into 10 power 38 times. Very, very large, right? So that is why your password system, for especially for banking, they are very, very safe. If you want to run through all these particular values, 2 power 128, this particular value, then hardly it will take more than maybe 15 years, 100 years. It might take for you to complete one cycle to check the password. So that is why there is a timeline also, that after maybe 60 days time, your password, your banking system will ask for a reset of your password. Why? Because by the time somebody runs a loop, you will again change your password. Okay, so that is the reason for having this 128-bit subscription. Okay, we will see more examples here. If say, for example, your n bit is 4, then the number of digits that are possible are 0 to 2 power 4 minus 1. So the formula is the number of bits for an n bit number system. It can represent the total numbers from 0 to 2 power n minus 1. Meaning if n is 4, then you have a combination from 0 to 15, right? So how did you get 15? So it is 2 power 4 minus 1. 2 power 4 is 16. So 16 minus 1, 15. Why it is minus 1? Because we are including 0 also. Okay, so that is the reason. Similarly, for 136, how many bits are required? If you want 136, the number of bits that is required, you can look at the same weight table. So 136 start from 0, right? So one position, second position. So the weights are 1, 2, 1, 2, 4, 8, 16, 32, 64, 128, and after this you will get 256. 256, you will go beyond 136. So how many bits are used to represent 136 is 1, 2, 3, 4, 5, 6, 7, and 8 bits are required to represent 136. Similarly, quickly, can you do an example? How many bits are required to represent a number 2, 4, 5, 6? Anybody quickly, can you answer? How many bits are required to represent 2, 4, 5, 6? I'll parallelly do. So it is 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, and 4096. 4096 will not come. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 bits. Anybody has got the right answer? I'm afraid to go to another window because I'm afraid my system will hang. However, let me see if somebody has responded. Nobody has responded. Oh, it will be where it will be in the comments. Okay, chat. System is super fast. Yeah, 12. Sanskrit. 12. 12 is the right answer. So you want me to explain it again, Sanskrit, Shreya? Shreya? You want me to explain it again, Sanskrit? Okay.
No, sir, I got the call.
Okay, good. Okay. All right. So, right. So this is how you will find out the numbers. So again, one more example. 175. How can you represent? The positional weights are 1, 2, 4, 8, 16, 32, 64, 128, and after this 256 will be there. So 256 is more than 175. So the number of bits required are 1, 2, 3, 4, 5, 6, 7, and 8. 8 bits are required. So I hope this is clear. So again, one more example here. The answers are in blue. Um, so these are the questions. Okay, so since the solution is already there, I can quickly go through it. So how do you represent a decimal value into a binary, octal, and hexadecimal? So decimal to binary, so this 29, you can use the positional weights, and 0.8, you will keep on multiplying it with 2, and you will get the coefficients. So that is how you will, so maybe I will do one example. Say if it is 29.8, so 29 though you can do with the positional weights, right? So how you can do with the positional weights? So it is 1, 2, 4, 8, 16, 32 will not be there because it's 29 only. So I will give 1 here, 16, 16 plus 8 is 24. So remaining 29 minus 24 is 5. So I can use this 4 and 1, right? So this will be 0, 1, 1, 1, 0. So let's see, verify it. We have got this 1, 1, 1, 0, 1, right? So we got the integer part. Now 0.8. So 0.8, I have to keep on multiplying it with 2. So 0.8 is 1.6. So I'll take only this coefficient 1. So it is 1. I'll take the remaining decimal part and multiply it with 2. I will get 1.2. One more 1 here. I'll take only the decimal part, multiply it by 2. It is 0.4. The coefficient is 0. Likewise, it keeps on going. So it is 1, 1, 0. We have already done. 1, 1, 0, it's already done, and 0.4 also. If you want, you can continue this. So it will be 0.8. So the coefficient is 0. Again, when you multiply it with 8, we are repeating this cycle here. We are again repeating, we are multiplying it with 0.8. So again, this cycle will repeat. So what will be the value? It is 1, 1, 0, 0, 1, 1, 0, 0. Likewise, it keeps on repeating. Okay, all right. And how do you convert this into octal? The formula is the same. You group into 3, you can convert to octal. You group into 4, you can convert to hexa. So likewise, do this particular exercise. Maybe later on I'll give you this. So there are additional exercises maybe you can take. What is the decimal equivalent of 1221 to the base 3? Okay. Uh, I'll discuss the solutions maybe in the next class. Since it is getting recorded, all what you can do is towards the end of, I'm going to wind up now. So this particular portion, you can go through this from the video. 1221 to the base 3, you have to find the decimal equivalent. Similarly, you have to add these two values. Please note that their base is 16. And then one more example is, this is a decimal value converted into hexadecimal value. Okay, so I do have the answers below. Maybe we will discuss in the next class.